In the previous video, we discussed the concept of mole. In this video, we are going to continue that discussion by talking about the molar mass. Both of these are very important concepts in chemistry that are used all the time. So it is important for you to truly understand them and know how to calculate the molar mass, starting with the periodic table. We can determine the numbers of atoms in our sample by weighing the sample and relating it back to Avogadro's number. How many atoms I have per unit mass depends on the types of atom that I have. Let's think back when we talked about how the atom is made. Where does the mass of an atom come from? The mass of the atom is concentrated in its nucleus, and it is based upon the mass of protons and neutrons. You can imagine then that as we go from one element to the next in the periodic table, we are adding one proton at a time, and we're adding at least one neutron at a time. One atom of hydrogen, therefore, weighs a lot less than, let's say, an atom of iron, because iron is much further in the periodic table than hydrogen, which is element number 1. You can also, based on that, you can also deduce that, let's say, a dozen atoms of hydrogen weigh less than a dozen atoms of iron or lead, because one atom weighs less and 12 atoms are going to weigh less than 12 atoms of lead. Following the same logic, then, we can say that 1 mole of hydrogen atoms weighs less than 1 mole of iron atoms. Now, they have the same number of atoms, but because each individual atom weighs less, for hydrogen that is, 1 mole of those, so collectively 1 mole of hydrogen atoms is going to weigh less than 1 mole of iron atoms. It's like saying 12 or dozen, right? A dozen feathers weigh a lot less than a dozen elephants. Why? Because 1 feather weighs a lot less than 1 elephant. Even though I still have the same number, so I have a dozen of each, the masses change because they're dependent on the individual atoms and how much they weigh. Similarly, right? 1 mole, we said, contains 6.022 times 10 to the 23rd atoms. So 1 mole of hydrogen atoms has 6.022 times 10 to the 23rd hydrogen atoms. But 1 mole of iron also contains 6.022 times 10 to the 23rd iron atoms. 1 mole of hydrogen, however, is going to weigh a lot differently than 1 mole of iron because individual atoms weigh differently. When we look at the weight of 1 atom, we measure that in AMU, or atomic mass units. Atomic mass units, once again, they're very, very tiny because it describes the mass of 1 atom. And we will, in the next slide, we will see how tiny 1 AMU is. When we, however, talk about the weight of 1 mole of atoms, we measure that in grams, and we call that the molar mass. The mass of 1 mole, or the molar mass. Not the mass of your molars in your mouth, but the mass of 1 mole of atoms. You can see that the weight of 1 mole of atoms is going to be a lot bigger than the weight of 1 atom. In fact, it is large enough that we can measure it in grams in a laboratory. However, because both AMUs and the mole are concepts that are related to the carbon atom, so by definition, they are related to the carbon atom, you will see that they're actually the same thing, but one is expressed in AMU and one is expressed in grams. And we will figure out how to calculate them in the coming slides here. When we calculate molar masses or even atomic mass units, we look to our trusty periodic table. So here in the periodic table, you will have, and there's variations of periodic tables, but the ones that we're going to use are going to have the symbol of the element, and then right underneath it, typically underneath, it's going to be a number that is not a whole integer. The whole integer is this number up here, 1, 2, 3, 4, etc. That's the atomic number that tells us the number of protons. The number at the bottom tells us either atomic mass units for one atom or how many grams a mole of that particular element weighs. So if I'm looking at hydrogen versus iron here, 1 mole, or let's just back up and talk about 1 atom. 1 atom of hydrogen weighs 1.008 atomic mass units. 1 atom of iron weighs 55.85 atomic mass units. And that is because iron has at least 26 protons and many, many more neutrons, whereas the hydrogen has only 1 proton and no neutrons. So therefore, 1 atom of iron weighs a lot more than 1 atom of hydrogen. Similarly, when I go to figure out how much 1 mole of hydrogen atoms weighs and 1 mole of iron atoms weigh, I will look at the periodic table and I get the same exact numbers, except they're not in AMUs, but they're expressed in grams. So 1 mole of hydrogen atoms weighs 1.008 grams. When I'm talking about 1 atom, it's 1.008 AMUs. When I talk about 1 mole, it's 1.008 grams. For iron, 1 iron atom is 55.85 AMUs. 1 mole of iron atoms weighs 55.85 grams. So microscopic versus macroscopic. And here is, we can do this for any element in the periodic table. We can look at any element, whatever's underneath it. If we're talking about 1 atom, that will be in AMUs, or if we're talking about 1 mole of that particular element, it will be expressed in grams. How are they related? Why is it that they're the same value, even though they're different units? Well, here's a calculation that shows you that. Okay, so I know if I'm looking at helium here, 1 mole of helium atoms weighs 4.003 grams. 1 helium atom alone weighs 4.003 AMUs. I also know, so going back here, I also know that 1 mole of helium atoms contains 6.022 times 10 to the 23rd helium atoms, Avogadro's number. So this is a conversion factor that we learned in the previous video. So if I start with this many helium atoms, every mole has this many, and then I multiply it by the mass of 1 atom. So 1 helium atom weighs 4.003 AMUs. Now I have this number in AMUs per 1 mole. And if I rewrite that down here, and I multiply it by the mass of 1 AMU, so 1 AMU weighs 1.661 times 10 to the minus 24th grams. Now you can see why these are so tiny, because it's the mass of 1 atom. So I have AMU per mole multiplied by the mass in grams of 1 AMU. So my AMUs will cancel, leaving me with grams per mole. And I get 4.003 grams per mole. Just like I have 4.003 AMUs per atom, I also get 4.003 grams per mole. And this is where it comes from. This is that particular calculation here. I just wanted to show you so that you can convince yourself that even though they're different units, this is for 1 atom and this is for 1 mole, they actually are the same value. The same thing is true for any of the other elements in the periodic table. I can do the same calculation for all the elements in the periodic table. So here are the things that you need to remember. 1 mole of that particular element weighs in grams whatever the number is underneath the element. We will really be looking at these numbers for the rest of the semester. We will not be dealing with individual atoms. This is important to know, but we're not going to be using them very much, the AMUs per atom. We're really going to focus on grams per mole, the molar mass, because it's macroscopic and we can measure it. So this is going to be important. And how many, so Avogadro's number, how many atoms do I have for 1 mole? So those two things are going to be important. Note that this is going to be the same for any atoms, any elements in the periodic table, or even molecules. We'll learn how to do those. This number doesn't change because it's like saying a dozen is 12. The same thing. This is the same whether we're talking about helium atoms, iron atoms, zinc atoms, it doesn't matter, or molecules of water, carbon dioxide. 1 mole will have Avogadro's number of all of the above. The mass, though, is going to change because each element weighs differently depending on the atoms that make up that element. And so we're going to have to learn to calculate the molar mass of different compounds depending on what the atoms are that make that up. If we're just talking about the element itself, not in a molecule, then we just look to the periodic table and we can get the mass that way. Now, to convert between mass and moles, here is the formula that we're going to use. If you are given the mass of the element and you are asked to calculate the moles, then you're going to take the mass of that element in grams and you're going to divide it by the molar mass of that element from the periodic table. So to go from mass to moles, you divide by the molar mass. If you have moles given and you are asked to calculate the mass, you multiply the moles by the molar mass. And we're going to be doing some examples just to get you familiar with how to use this formula. But this is important. We're going to be using it all the time. Here's a sample problem. Determine ABC, the number of moles of carbon in 25 grams of carbon, number of moles of helium in this much helium, number of moles of sodium in this much sodium. I am going to work A for you, and then you can try B and C on your own. When we do these calculations, we better have our periodic table handy because that is where we're going to get some of the information that we need to be able to solve these types of problems. Here's our calculation or periodic table. I find where carbon is, and right underneath the symbol, what do I see? I see the molar mass. So 1 mole of carbon weighs 12.01 grams. That is my conversion factor from grams to moles, and I get that from the periodic table for each element. I find carbon. You're going to find the other two, sodium and helium, I believe it was, and you will find the molar masses directly underneath the element symbol. So I know that 1 mole of carbon weighs 12.01 grams. So here's the problem again. Start with the amount that you are given in the problem, which is 25 grams. Never start with the molar mass, or you will make a mistake. So write the amount that you are given, 25 grams, times. Okay, I want grams to be on the bottom and moles at the top because that is what I'm asked to calculate. So I write my conversion factor as a fraction where I have 1 mole of carbon weighing 12.01 grams. Note that 1 mole, for the molar mass, you will always have 1 mole and then the number that will go with the grams. A number larger than 1 will go with the grams. But this is only for the molar mass. So when I write my molar mass conversion as a conversion factor, 1 will go with the moles, and then whatever the number is under my element will go with the grams. So I cancel my grams, and then I have 25 times 1 divided by 12.01, giving me 2.082 moles. Note that my answer has 4 significant digits because my number here has 4 significant digits. This is considered an exact number because it is my conversion factor. We do not count these numbers when we look for significant digits. Only the measurement, and this has 4 digits because that decimal point makes these trailing zeros significant. I have 4 significant digits here, therefore my answer will have 4 significant digits. I will give you a little bit of time to try to solve B and C. Work them just like we did this example. So look up what the molar mass for helium is and the molar mass for sodium. You will find them right underneath the symbols for each, and then set them up very similarly to what we did here. Now here is kind of a schematic that will help you figure out how to get from one to the other, to interconvert between grams, moles, and atoms, numbers of atoms. Once again, I suggest that you either have this written somewhere in your notes where you can find it all the time or print it out as well. If you are starting with grams, follow the arrows. What does the problem give you? So if it gives you grams and it wants you to calculate atoms, first you divide by the molar mass to get the moles. You know how to find the molar mass of that element because you find it right underneath the symbol. So you start with grams, you divide by the molar mass to get the moles of that element. Once you know the moles of the element, all you have to do is multiply by Avogadro's number to get to how many individual atoms there are in that sample. Note that there is no direct way to go from grams to atoms. You have to first convert to moles because there are conversion factors that will relate grams to moles and atoms to moles, but not directly from grams to atoms. Now, what if you start with moles and you want grams? Well, all you have to do, follow the arrow. You multiply by the molar mass to get grams, or you multiply by Avogadro's number to get atoms. If you start with atoms and you are asked to find moles, you divide by Avogadro's number to get the moles. And then, if you are asked to continue to figure out grams, you take the moles and multiply by the molar mass to get to grams. Here's a sample problem. I will work A for you, then you can work on B. Determine the number of carbon atoms in 0.515 grams of carbon. Use your little chart. You are starting, so determine first of all, where do you start? You are starting with grams and you are asked to figure out atoms, right? So we are here 0.515 grams, and we're asked to figure out the number of atoms. So what are we going to do? We can't go directly from grams to atoms, but we can go to moles. So we can take grams, divide by molar mass of carbon to get the moles of carbon. Once we have the moles of carbon, all we have to do is multiply by Avogadro's number to get the atoms. And here's kind of the setup for you, right? So once you have the moles, you will have a number here, multiply by this conversion factor to get the number of atoms. So what's it look like? Well, here we are. We have 0.515 grams of carbon, and I'm converting it. I'm doing it all in one step, but this first conversion factor is converting to moles. So 1 mole weighs 12.01 grams. We saw that from the previous problem from the periodic table. So my grams of carbon are going to cancel, and what do I have? I have 0.515 times 1 divided by 12.01. That will leave me with moles of carbon. Then once I have that, to convert to atoms, I multiply by the Avogadro's number because I know that 1 mole of carbon contains Avogadro's number carbon atoms, so 6.022 times 10 to the 23rd. My moles will cancel, leaving me with atoms. If you want to do this all in one step, like it is here, then your grams will cancel, your moles will cancel, leaving you with carbon atoms. So you would take 0.515 multiplied by 1, multiplied by 6.022 times 10 to the 23rd, then divide that by 12.01, and you get 2.58 times 10 to the 22nd carbon atoms. Note, you can double check yourself. Figure out if this answer makes sense. Note that this power is less than 6.022 times 10 to the 23rd. It's to the 22nd. And it's approximately half, which makes sense because this is about half of that amount. Okay, so if this came up to 24th or 25th carbon atom, so larger than Avogadro's number, then it would be a little, you would know that this is wrong because 1 mole weighs 12.01 grams, but I don't have 12.01 grams, I have much less. So my carbon atoms are going to be much less in my sample of 0.515 grams than 6.022 times 10 to the 23rd, which are contained in 12.01 grams. And actually, I said about half, but it's actually a lot less than half. I was thinking a half a mole, but this is 0.515 grams. Okay, I will give you some time then to calculate the mass of helium that contains this many helium atoms. Here, you are starting, you're kind of working backwards than what we did for this problem. So you start with helium atoms, and you first convert to moles of helium, and then calculate the mass of helium. Use your little flow chart to help you and to guide you in doing these calculations.